15 hours. We should be okay. I was going to check the memory every so often. Every so often I check and it's like 2 minutes. I'm like, ah. So as you guys know, next week we have test 1. So we'll start with test 1 next week at 5, and then it won't take the whole time. And depending on weather conditions and other junk, we may or may not have lecture after that. All right. If we don't have lecture after that, then I owe you a couple of videos to stay on track. But I think it'd be good to have lecture afterward, actually. But test 1, it covers missions 1 through 5. I will tell you, like, so on mission 1, there was some kind of cultural enrichment problems about hyperbolic geometry. I would not anticipate those being on test 1. Those are kind of outliers. They really just were isolated calculations. And they also involve an abstraction that we haven't really focused on in terms of like talking about a non-standard distance function, right? So I wouldn't worry too much about those. But you do need to know how to do like basic calculations with vectors and vector fields, differential forms, paths, curves, a little bit about the push forward, right? Because that was in mission 5, right? That problem I was just helping you with, Maya. Let's see here. And then, of course, like, you know, setting up the frame correspondence, like finding an isometry which maps a frame at a point to another frame at another point, like we did last class. That's a, you know, calculational skill you want to kind of have in mind. You should be able to derive the Frenet-Serret equations like we did in class. It took me about an hour, right? So it's probably not, I'm probably not going to ask you to derive the whole thing, but I might say like derive, I might have some subset of that derivation. Certainly the main idea in that derivation is what? Is that the TNB forms a frame. So whatever vector we're looking at, we can form like vector dot t times t plus vector dot n times n plus vector dot b times v. That, you know, breaking the vector into a sum of its orthogonal components with respect to a frame, that's an identity we've used again and again and again. Like, Audric, I was talking to you earlier, we use that for that connection coefficient problem, right? Like, it comes up in problems you don't expect. It's a tool that we need to be ready and willing to use, this idea that if we have a frame, we can expand a vector in that basis. That's an important calculational idea. Hey, welcome. Let's see here. Of course, you need to know, you know, how to calculate covariant derivatives. Like what's, and you got to be aware for the covariant derivative. So if I have the covariant derivative of v in the w direction, then we said that that was the sum. I mean, this was not the definition, right? But this was a nice formula. Sum I equals 1 to 3 of v of wi ui, right? Like this was a very helpful formula. Now the definition oh man, I forget. The definition was given in terms of differentiation of a curve, if I remember right. But, well, let me just say this. This is actually how I tend to calculate the covariant derivative. Most of your homework problems, you could do them that way, right? And let's see here. However, this is for w equal to, you know, w1, u1, w2, u2, plus w3, u3, right? Now, if we had w equal to f1, e1, plus f2, e2, I like to put the numbers up on these. O'Neill and I have some stylistic differences there, right? But if, and E1, E2, E3 is frame, right? With, how did we define it? Omega ij of v equal to covariant derivative in the v direction of ei dot ej, right? Then what's the formula for covariant derivative? In that context, the covariant derivative looked a little different, right? It was the sum I equals 1 to 3 of v acting on fi plus the sum j equals 1 to 3 of f upper I omega I j, oops, excuse me, well, oh man, now I have forgotten. You guys help me out here. If I want to include this, if I want this to be EI like that, I can't remember if the sum here, yeah, I mean I can, well if I do I like that, I guess I need to make this a J. Well, if I'm going to put the J sum out here. That makes this a J. I think that's right. I'm not 100% sure about the... I. Okay, so this is the formula that we have for the covariant derivative with respect to a non-Cartesian basis, right? It's a little bit surprising. It involves the connection coefficients. It's kind of a pain, right? But one of the things you should be able to do, this was a homework problem, right, was to derive that formula. And I think it's one of the first things I did in class too, right? Kind of badly, but at the end of class one day I did that when I first introduced the covariant derivative. Now, how do we actually calculate the connection forms? Like, what was the good way to do it? So remember, if EI or E1, let's say, equals to A1, 1, U1 plus A1, 2, U2 plus A1, 3, U3, and E2 is A2, 1, U1, A2, 2, U2. My apologies for all the writing. A2, 3, U3, and E3 equals to A3, 1, U1 plus A3, 2, U2 plus A3, 3, U3, then these coefficient functions form the what? What is this matrix called for the frame? This is the so-called attitude matrix, right? For the frame E1, E2, E3, right? And so if you have a non-Cartesian frame, we also proved what? We proved that the, remember this theorem? the connection form, right? What's it equal to in terms of the attitude matrix? What did we get? Mm-hmm. So I'll remind you, what we had was dA A transpose. Where did that come from? Do you guys remember the derivation of that? How did we derive this formula? So those are the structure equations, but this is before that. I mean, those are good. Those are also potential test questions. So Audric was just reminding me that. Well, I'll get to that in a second, okay?
Summation from K equal 1 to 3 covariant of V on I, AI, K, UK. No, I just restated what you said.
Hmm?
I got the proof, got EI, and it's just that matrix you just did.
Mm-hmm.
We derived it from the covariant derivative of the summation of K equal 1 to 3 A, I, K, UK, dot EJ.
So
That second part.
this one here.
Well, yeah, but we got V of A, AT is equal to EA of V, A transpose.
Right. That is the one. So it was omega ij of V. What was it equal to? It was equal to, well, by definition, it's equal to covariant derivative of V EI dot EJ, right? Right? And then what I did was I took the EI and I wrote it in terms of the Cartesian basis and the attitude matrix. So this is the covariant derivative of V sum over, let's say, K of A, I, K, UK, dotted with what? Dotted with this, yeah, EJ, which I'll write is the sum over, or did I leave that EJ? I'll leave it as EJ. How about that?
It was the sum over something
Yeah.
of AJ1 through 1.
I'm going to leave it as EJ, and I'll show you why in a second here. So the covariant derivative we can pull out. So what else should you know? One of the things we should know for the test, of course, is properties of the covariant derivative, right? So we had a list of like 6 of them. You are allowed a sheet of notes for the test. Okay, so front and back, one page, yeah. So we have a covariant derivative in the v direction of aik uk, right? All of that, all of that. I mean, you put the parentheses before or after the sum, whatever. After all that, we take dot ej, right? Okay, fine. Now, this is a vector in Cartesian form. So we can fall back, if you want, we could just go straight back to our basic thing, which was the covariant derivative of a vector field in Cartesian advanced basis. We just take v and act on the formula. So that's the sum over k of v acting on aik, all right, uk dot ej. But you know what uk dot ej is? No, these are, so it's a Cartesian basis versus the non-Cartesian frame. So it doesn't have to be Kronecker delta, but see this here? We have, by definition, EI is what? Or EJ, it's the sum over L of A, JL, UL. Right, that's the definition of the attitude matrix. So, oh, you already got it. It's cool. I didn't see you move it. Anyway, so this is straight up what? This is exactly a what? A K dot product with E, see dot with K, so AJK actually, AJK, right? So if I take dot product this formula right here with UK, what happens is right, that's Kronecker delta, KL. And so that squashes the finite sum and just leaves us with a JK, which is what I said over here. But so we have then is sum over K of V A I K A J K. Now, we have one of the other fundamental things we need to know, and just a reminder, is df acting on v, what is it? That's v acting on f, right? This is how the differential of a function on a vector field works. So this is a vector field acting on the function aik, right? I can rewrite that as daik acting on the vector field v. And then I still got the, well, I'm going to rewrite it A transpose kj. Now at this point, I have the right index structure. I've got k matching k, I and j here. So what that is dA, dA acting on v times A transpose the ijth component. And since that identity is true for all ij and for all v, we write the formula that I have written on the other board. See, that formula I boxed in, the theorem I claimed, this right here is a shorthand for the formula that I'm drawing an arrow from. Anyway, all I'm trying to really tell you here is this little innocent-looking boxed formula here, there's a lot that goes into this, right? I mean, it's kind of a pain to derive. But once we have it, it gives us a nice way to calculate the connection coefficients for a frame, right? Because it's a pretty straightforward business to take the exterior derivative of a matrix and multiply by another one, right? Like, it's not that bad. Now, the next chapter in that story was that we could talk about a coframe, right? Theta 1, theta 2, theta 3, right? And the coframe, so these are elements of the one forms on R3, and they're dual to the frame in the sense that in the sense that theta I of EJ is Kronecker delta IJ. All right? And so we said we'll let theta be this vector of covectors, or of one forms really, theta 1, theta 2, theta 3, right? And we had d zeta equal to dx dy dz, right? And one of the things we worked out, we saw that d zeta, right, was equal to a times theta, right? So we saw that, right? And then we were like, oh, well, that's neat, because we can take exterior derivatives of this and use the calculus of matrices of forms, and when we exterior differentiate this, what we get. Right? But the thing is, d zeta was 0. And let's see here. What else do we have? Okay, so 0 is that. I might have started wrong here. I don't know. I do know that I can take this here, and I can rewrite this as dA, A transpose A, right, wedge theta. Because A transpose A is the identity matrix, right? So we can put in the identity matrix and not change the expression, right? And if you do that, then what's this piece? Well, this piece is omega. And what's this piece over here? What's that? Yeah, theta, right, exactly. Well, A wedge theta, what was it? Did I write this right? Oh, that's d zeta, right? Wait a minute, no. A theta. I'm sorry, I seem to have veered off the beaten track here. Just a second, let me. See what kind of damage I have done. Oh, I've got it backwards. I'm an idiot. I've got it backwards. Look, this is wrong. This right here, this is what's wrong. It's the other way around. It's that theta is equal to a d zeta. Sorry about that. So what that means is that the coframe is related to the dx, dy, and dz in the same way that the frame is related to u1 and u2 and u3. And then that we differentiated. We got d theta is equal to dA wedge d zeta, which is dA a transpose wedge a d zeta. And dA a transpose is omega, as we were just deriving, and a d zeta was theta. And so there you go. That was the first Cartan structure equation. I knew I was doing something wrong with the other way, so like, oh, idiot. Me, not you guys, right? Obviously. But and how did we get Cartan's second structure equation? Remember, we know A transpose A is equal to the identity, right? For an orthogonal frame. And then take the exterior derivative of that. Remember, A is a matrix of functions here, typically. Now, in chapter 3, when we actually find A for a specific, like, isometry or orthogonal transformation, there A is constant. So, like, this stuff becomes really, like, stupid in chapter 3. But for a general frame, like a spherical frame, for example, has a coordinate dependence, these exterior derivatives are interesting. So anyway, this is dA transpose A plus A transpose dA equal to 0, right? And what's that tell us? I guess that tells us that we could solve for dA, right? dA would be equal to minus a dA transpose A. I'm not going the right path here. Oh, of course, I mean, fine, whatever. This is not wrong, it's just not. Right. I think we have to go back to here, right? We have to start with that. Omega is dA. Right, so d omega is d of dA, right? Right. And then minus 1 to the what? To the degree of dA. What's the degree of dA? It's 1. Because dA is a matrix of 1 forms. Okay, dA wedge dA transpose. Okay, and now the first thing, of course, is 0. But then over here, we have minus dA well, we can trade dA. I guess I'll keep the dA. dA A transpose, right? A dA transpose, right? So the first one's omega, right? Minus omega.
Yeah.
And then this is wedged with minus A transpose. Good grief.
You got minus dA of A transpose, which A dA transpose, and you got minus omega wedge minus omega.
Yeah, I mean, I think I need this. So if we have A transpose equals to I, we exterior differentiate it, and that tells us that A dA transpose, this guy right here, is actually equal to what? Minus dA A transpose, right? So I can trade A dA transpose for minus dA A transpose, but dA A transpose is omega again, so we get minus omega wedge minus omega, which is omega wedge omega. There you go. This is Cartan's second structure equation. So there's Cartan's two structure equations, right? D theta is omega wedge theta, and d omega is omega wedge omega. Just thought I should go back through those again briefly, mostly as a showcase of the calculations we can do with some of these things. Now, I think there's like a more basic question. I shouldn't forget to talk about the Frenet-Serret equations, right? I mean, I mentioned that you should be able to derive those, right? But you should also just know them, right? And you should be aware that they look different whether we're using a unit speed curve or a non-unit speed curve, right? You should be able to calculate the curvature and the torsion, the speed, velocity, acceleration, all these good stuff for a curve. I think those make pretty fair test questions, you know? You might have been able to do those before you took anything, before you listened to me talk about anything. I think Dr. Rekovich covers that stuff in Calc 3. So you may already have some, familiarity from there. But so that's one thing. Is like you should be aware of, how to actually calculate the TMB frame for a curve, right? You should be aware of some of the basic theorems we had. Like if I tell you that the torsion for a curve is 0, what can you tell me about that?
Well, we have to prove any theorems.
Prove any theorems? I mean, if I proved it in class, then it's fair game. But some of the proofs I've done in class, like there's a lot of setup. So for example, proving that a curve is planar if and only if the torsion is 0. One direction of that proof is very reasonable to ask anybody. The other direction involves this very kind of ingenious construction of a particular function, which then you show the function as derivative 0 and therefore must be constant. And the constancy of that function gives you the planarity of the curve. To me, that step, that creating that function, which means that's a pretty ingenious step. And if I was to ask that proof on the test, I probably would ask the question in the format, consider this function, show it's constant, explain to me what it means about the planarity of the curve. I would probably walk you through part of the proof if I was to ask that. The flip side of it, assume the curve is planar, show that the torsion is 0. That's taking candy from a baby. That's easy, comparatively speaking. There are some things I'd like you to be aware of, but I wouldn't expect you to prove. Like, for example, if both the curvature and torsion of a curve are constants, what's that tell you about the curve? It's smooth. No. Well, it's a helix.
Is that like one of our homework?
No, that wasn't a home. That's a theorem in O'Neill that I did not prove. In fact, if you look in O'Neill, there's a section where he has some deeper results about curves using the Frenet-Serret technology. And I haven't done everything in there, and certainly if I haven't done something in there, I wouldn't probably test you on it. If there's a homework problem, then, the other thing that's kind of outside of O'Neill is when we were first starting, I was giving you guys tangent space and normal space questions, remember? So I might give you one that's very similar to one of those again, since we've spent so much time on that, right? Mm-hmm. It means, yes, I mean, that is true. It means, or b prime dot n is 0, right? But ultimately what it means is that the curve lies in a plane. So it's a planar curve. Because what torsion describes is like the lifting of the curve off the osculating plane, right? You can fit a plane, the osculating plane is because that's where the osculating circle is the one that fits to the curve, and the center of it, the Frenet normal points to the center of it. The radius is the reciprocal to the curvature at the point. That's the osculating circle. I have not given you guys a homework problem on that, have I? Right. But I did not give you guys a homework problem on that. I almost did, but then I thought, it is kind of a pain. Like if you look in the solutions to the homework that I've given you, you'll notice that there's a problem in there that involves the osculating circle and constructing it. And it's something we could do, I just didn't do. So, other thing, like just situational awareness, like ask yourself the question, should I be writing this? Does it make sense? Right? So like some things. First of all, df, like I was just saying, we have a function from, whatever, Rn to R, df of v, we have shown or defined, whichever way you want to look at it, that df of v is v of f. So we know this, we can use it, all right? Another thing, so v is, let's say v is a vector field. So that means that this is a derivation on functions of R3. We can look at it that way. But what that more specifically means is you could expand V as like V1 partial x, right? Partial y, V3, right? Or the O'Neill notation, right? This is a vector, right? And then sometimes, and I'm okay with this in as much as you don't get in trouble with it for the problem that you're given, what's the other way we write this? Which is super abusive notation, but what's the other way we write this sometimes? I think sometimes we write this like this, right? We're especially guilty of that in our study of the Frenet-Serret equations, right? Like the velocity vector, you guys have all done this, right? If alpha of t is t squared, t cubed, right? Alpha prime of t, what was it? 1, 2t, 3t squared, right? When you do that, you're using this abusive notation because we also do mean that this is equal to u1 plus 2t u2, right? Plus 3t squared u3. So like, is it a static vector? Is it a differential operator? Like, which is it? The answer is yes. We use both notations and we interchange between them as whatever it takes for the formula to be reasonable. That's the sort of ninja way, if you will. I mean, it's our MO in differential geometry. That's how people operate. It's not great. I mean, it would be better if we always imposed some kind of correspondence and wrote things in terms of the correspondence and made explicit when we were using the different viewpoints. I could do that, but then you would have a really hard time reading O'Neill. So my point is, feel free to use this notation where it is the right notation, right? For example, in calculations for the Frenet-Serret stuff, obviously that's the right notation, right? If you're proving something that involves this identity up here, this angle bracket, wrangle notation, it's not going to help you. Not a little bit, right? And so like when I have something like, for example, dx acting on, let's say, v, right? And v is the vector, I would strongly discourage writing this, you know? Like that is not helpful. I would just go straight to, well, that's v on x, right? And then I would say, well, that's v1 partial x plus v2 partial y plus v3 partial z acting on x, right? So what I'm trying to say is if you're dealing with a formula where the vector is acting on a function, think of the vector as a differential operator. If you're not, maybe don't, right? There are other problems where we had to think of the vector as like the derivative of a curve. Problem 37, I think. The one that set up the other, anyway. So what happens here is what? Yeah, that one. Covariant derivative alpha prime of t, w, is equal to w sub alpha prime of t. Like that is really born of the equivalence class of curves view of vector, truth be told. Anyway, getting back to this calculation here for a second. So we had plus v2, upper 2. I try to write my upper. v2 partial x partial y. What's partial x partial y? Well, partial, yeah. What is partial x partial y? I heard 0, right? Partial x partial z, 0. Partial x, 1. Right. So this was the calculation I wanted you guys to do at the start of mission 3. None of you did it, right? And that's okay, as long as we can fix it now. So dx acting on v is straight up the first component of v. That's all. Now, this means, by the way, that we can play some other games. Like, check this out. If I have a vector field like so, I can expand it like this, right? V is equal to what is it? It's equal to the sum, I equals 1 to 3, of dxi acting on v partial xi. This is an okay thing to write because this is a function, right? That is itself a function. Because what is it? It's a vector. I mean, like when you work it out, if you look at v of xi, what is that? I mean, v of xi, you're hitting this coordinate function, the ith coordinate function, you're feeding it into the differential operator, right? And when you take those derivatives, it just gives you back functions, or a sum of functions, whatever appears as like the coefficients of the v, the v1, the v2, v3. I mean, that is literally v1. So that's another way we can look at the vector field. But, so like some of you have mentioned, like I was doing a calculation, I found something like I had u2 times u3. Like if you find yourself writing something like that, that means something has gone awry, right? We should not have formulas that have u1 dot u3, that's fine. But just multiplication of vectors, just straight multiplication, that's not something that we've we've run into. Now, the other thing, continue this walk down memory lane here. One form, right? So alpha a one form, what's that mean? That means you can write alpha as something like alpha 1 dx plus alpha 2 dy plus alpha 3 dz. In 3 dimensions, that's what a one form looks like, right? And one forms are also naturally viewed as alpha basically is a function. If we fix a point, alpha at a point, it's a function from the tangent space at that point to the reals. Now, if you don't fix the point, if you allow the point to vary, right? If we look at alpha of v, then this is itself a mapping from R3 to the reals. Alpha of v itself, this is actually a smooth function of some sort or another. Like, let me give you an example. If we had alpha as x squared dy minus y dz, right? And if I have the vector field v equal to x plus e to the x, e to the y, let's say, dx, listen to me, partial x plus the tangent of z partial y, right? So there you go. There's a one form, and there's a vector field. We can calculate alpha of v, right? And if you believe the homework problem I had you do in mission 3, we could just write down the answer. All right? I won't do that. I'll actually go through it and work out the details here, but here it is. So we have x squared dy minus y dz, and I'm going to leave that as v for the moment. All right? Because writing out the details of v at this point does not help me. It just makes me write more. Now, this, by definition, is x squared dy acting on v minus y dz acting on v. But how do we make sense of dy acting on v or dz acting on v? Go back up to this, right? Think of y being the function, or z being the function in question. So this is essentially, by definition, x squared v acting on y minus y v acting on z. Right? But what is v acting on y? And what is v acting on z? Those are exactly the y component and the z component of the vector field v. What is the y component of the vector field v? It's what? Oh, you're looking at the form, but the v, not the alpha, the v. So what's the y component of that one? Tangent z, right? So tangent z is this. And of course, you could differentiate it and find that. You could let v, this derivative, act on the function y, and what would happen is you get partial y, that's 1. You pick that up, this is 0 when y hits it, when it hits y rather. And what's the z component? There's one, right? So the answer is x squared tangent z. Now there was one problem in the homework where it was like this, but O'Neill fixed a point, and he made us calculate like a form at a point, evaluating a vector at a point. it's really the same calculation. It's just you're evaluating functions at those particular triple of numbers. But if you really drill down into the calculation, it's the same as what I'm doing. And look, this is exactly that homework problem I told you. It's alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. So like when you take a form and you evaluate it on a vector field, you end up kind of just taking dot products of the components of the form with the components of the vector field. That's what intuitively is going on. See that? So like there is no matching, and this has an x component, but that one doesn't. So the x with x, that alpha 1 v1 term is 0. This one has a y, but this one and that one both have y's. So that's why I get x squared tangent z. That's just coming from this alpha 2 v2 term. And alpha 3 is minus y, but v3 is 0. So that's why this term doesn't matter. So all of the formula is coming from the middle one. This was the intention. What I'm telling you right now was I wanted you to pick up this understanding from mission 3, the new problems I introduced at the start of mission 3. And I don't think they serve that purpose. That's why I'm taking class time right now to do this. I hope this helps. Yeah, it's not bad. It really isn't. It really isn't that bad. And so when I first start talking about differential forms, I'm not talking about them as operators, right? When I introduced the, you get some bad energy. Uh-oh. It's like it wasn't. Somebody must sell something that's like bad mojo or something, you know, probably. When I started talking about wedge products and differential forms, I wasn't like talking, I didn't remember, at no point did I tell you, like, let a 2 form act on something, or let a 1 form act on something, right? I just introduced them as like abstract objects that we can do algebra and differentiate on, right? Later, all of a sudden, we're talking about differential forms acting on vector fields. So that was what O'Neill introduced later. Like to start with, I just talk about differential forms as abstract objects that follow the same like algebraic patterns as calculus 3, as we saw. So if you feel like there was kind of like a bait and switch, I mean, there's a cognizant jump between what I was doing originally and then what O'Neill is doing. You're right. It's because to start with, I wasn't letting differential forms act on other things. But there is a way. So there's a natural way to let differential forms act on vector fields. All right. So a differential form can act on a vector field to give us a function, like alpha of v, like we're just doing. We'll see as we study chapter 4 that you can take a 2 form and evaluate it on a pair of vector fields to get a function. So like 2 forms don't just take in 1 vector field, they have to take in 2. Anyway, this is one of the hurdles to understanding differential geometry that we all face as students, like to start with, is understanding how we can take a given object and sort of contract it, or in some sense multiply it against another object. There's like a lot of different ways to do this sort of thing, and anyway, it's something you have to kind of keep poking at until you eventually understand. But anyway, of course, the purpose of the course so far, we studied just the general setup, right? Then we studied a lot about when things are perpendicular and about how we can use that perpendicularity to derive things, right? Like the orthogonality has played a big role in the Frenet-Serret derivation, you know? And we've discovered the curvature and the torsion can describe a curve up to congruence, right? And then we even, in chapter 3, saw how to build that congruence from an isometry, right? Using the attitude matrix stuff again. So I should have the solution to mission 5 posted like a little bit later this week. You're welcome to give me it. It'll get to me by Friday. It should be, honestly, like you could give me mission 5 next Monday if you wanted to, but it'd just be better for you if you gave it to me Friday, so you have a chance to like absorb my solution to mission 5. But if you can't get it to me to Monday, it's okay. I understand. It's for your best to have a chance to kind of, you know, take a step back and absorb the solutions that have been written. So like, I think last time I gave a test in here, not in here obviously, but last time I gave a differential geometry course, I think my test one, among other things, like one of the questions on there was derive Cartan structure equations. So I do think it's a good test question, that stuff we did over there, because it's relatively sort of symbol pushing. I think finding the attitude matrix for a frame, that's not a bad question, right? So if I can give you a frame, I give you the frame, and then say find the attitude matrix, find the connection coefficients, like that's a decent problem. It's kind of it's not too much calculation. Of course, find the Frenet frame and the curvature and torsion for a curve. That's a pretty good question. And then there's various sort of like second level questions. You saw one of these in the homework that involve applying the Frenet-Serret equations to prove various things about the geometric quantities, curvature, torsion, and so forth. I am so annoyed that other day that I derived the formula for the jerk. There's a jerk formula for the torsion. It's like alpha prime 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 dotted with alpha prime cross alpha prime prime divided by the length of alpha prime cross alpha prime prime squared, something like that. This is the torsion. And we derived it in class using like a particular, like we differentiated the formula for acceleration. There's an acceleration formula which has dv dt t plus kappa v squared n, and we differentiated that. And differentiating that would give you alpha prime 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 equals to stuff. And we were able to look at that stuff and notice that the b component was a particular thing. And so if we took the dot product of alpha prime 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 with alpha prime cross alpha prime prime, blah, blah, blah. I said it all in words, and I wrote it in this board. I never panned to the board where I wrote the steps down. It's killing me. That would make a very good test question. So, sorry. Is it too soon? Is it too soon? Yeah. Dr. Cooks can be a jerk on the test.
How many questions?
Enough? That's an easy question, yeah. Enough if you know what you're doing, too much if you don't.
And you're setting it
It's probably 5 or 6 pages. Usually I leave white space to work on the pages,
So probably just nice homework.
Oh, definitely more. I mean, I think the homework's just been, did I space about the homework? You may be looking, I have done it for Calculus 1, so like, that's what you're messing with my head. The test should be shorter than any of the homeworks. Shorter. Goodness, yes. So
with the attitude matrix, is why, like I remember in linear, we would call it the matrix of coefficients. Is there a difference, like?
Oh, sure. There's a rather large difference in the I think the weather's okay. We'll stick it out here tonight, guys. I don't. Does it feel? What's the temperature outside right now? Can somebody do a spot check on it for me? 34. It usually has to drop about like 10 before anything. No, okay. We should be okay then. So, Audric asked me about linear algebra, basically, right? So.
Because it looks like just a coefficient.
Oh, sure. So in linear algebra, we're typically solving something like a11 x1 plus a12 x2 plus a1n xn equal to b1, and then so forth and so on. You have m equations and n unknowns, right?